Hello there. Welcome to another problem session. So today we have an interesting problem. We found a formula for L in the last video for a coil like this, where inside of the coil did not have a magnetizable material like iron or something like that. So we were just dealing with just a coil. Inside is like a vacuum or just non-magnetizable material, like a plastic, and you just coiled it. So we have a formula for that. If you have a magnetizable material, you'll have some multiplier to that formula that I'm going to go over in a future video. But right now, we're going to carry on from that video. So now we have the same circuit as the last video, but now we want to know what is growth in the current, how the current grows in this circuit. So when you turn this on, it doesn't immediately become the full current. It actually takes time, and that's called inductive effect or self-inductive effect. And the equation that this will follow is called equation of motion of this dynamic circuit. So there is no Kirchhoff rule or law, etc. for this circuit. Okay, I know there are some other engineering books use Kirchhoff's laws, try to kind of use the analogy. But what we're going to do is we're going to always use Faraday law. So whenever you have a dynamic circuit, you should always think there is Faraday law, because when the electric field is changing, the magnetic field is induced, and you can see there's a in the dynamics you are going to have electric field changing. So you should always think of Faraday law. So what is a Faraday law? You have minus E dot dl. I like to think this oriented. So this is some kind of, this loop has an orientation, is d by dt. And so this surface is also oriented. Use a right hand rule. So this C and this have a relationship of right hand rule. And then you have a B dot n hat. So this surface and this n hat are related. So this right hand rule, dA. And this whole thing, because I pull the minus out here, you can call this EMF induced in the circuit. So this is the Faraday law, and we've been working with this in various problems. So if you know how to do this using Faraday law, that's great. If you know some other way of doing this problem, go ahead and try to do this problem. So when I say find an expression, I mean actually from the laws that you know, not just memory, you remember the answer. So for instance, the answer for A will be something like I of t is going to be V naught over R, 1 minus e to the power minus R over L T, something like that. So if you know from memory, I don't mean you give me this formula by memory. I mean derive this kind of formula. You want to see if it's L over R or R over L. Is it L over R? Is it R over L, etc. You know, this one you can guess it because this just from the units. There's a V0 and there is a R, and so there has to be a ratio of them, which becomes like a current in terms of units. But the rest of them, you really have to derive it, okay? And you can derive it using Faraday law. So once you have this, answering this question, second question is very easy. So this will be like a maximum for this expression, and then so this is the I maximum. Let's call it I max. So I want T, but it is 90%. So this is 0.9 I max. equal to IMAX, like this. So IMAX gonna cancel it out and solve for t. So that's gonna be the strategy. Okay, so if you know how to do it, go ahead and do it and come back and check with my answer. All right. Okay, so I'm going to do Faraday law. So when I go around this whole loop, I am going to go around in a direction in which the positive current is going. All right. So we are going to go in that direction. The DL will be in that direction. And so right-hand rule, the B that's going to come out is going to come out like that direction. That's the B direction at time t. And it will be, I'll just say all of these B's are just parallel and I orient it, and then there is a B, I comes this way, so you have a little B going like that, and little B going like that, and we kind of ignore the ignore in this area, but we don't ignore in this area. And see previous video on self-inductance. Okay, so I'm going into this, and that's the you can actually separate out for your calculation's sake this loop into a self-inductance part and a resistance part. So it will look like this. So I have just resistance and just L, and then sometimes we draw it like that, and it's kind of very little bit deceptive. I like to go like A all the way to C. That's basically what's going on is electric field as you E dot dl. There's going to be local voltage drops. If you're going in the current, same direction the current, you have a local voltage drop. So you are going to have this left, I'm going to call this left hand side and call this right hand side. And so if I just one circuit like this, we know this is equal to L di dt that's going through this circuit. This current is the current going through the circuit, and here you have to the sign is very important. If you're doing all of this, if you C and S, this n hat is correctly gotten, then you'll have a positive relationship. So basically n hat, this is positive if n hat, which is n hat is this way here, n hat is in the same direction as B. So the sign is very important. Actually, people can mess up the sign. So let's do it from I go this, and then only thing I encounter with in the left hand side equal to minus A to C. I go like that, E dot dl minus C to A, E dot dl. Now this is the volt. If I put a plus, this is the voltage drop across going over there. So this actually picks up the voltage. So this will be plus V. And when I go over here, this is the voltage drop because of resistance. So this can be written as minus I and the R in the entire circuit. So this, if you're looking at over here, you can think of this as no R, and then this one is L, is 0. So this is the R part, so this is the only part that's going to be. So if you're thinking A to C, in this diagram, this effect, this is not the real diagram, this is the actual physical things happening. This is the property separated, R separated from L, but they're actually in the same material, so it's not, you can't separate them. So this is going to be minus IR, and this is going to be plus, this is going to be V0 on that. So left hand side is just equal to minus IR plus V0. The right hand side is just whatever L of the circuit is, L of the circuit, which is mostly coming from here. There's a L from other parts also, but we ignoring that, it's mostly coming from here. In here, we just include everything. So this L is L of the entire thing, okay, the entire circuit. Okay, so this right hand side will be just L di dt. Now you can see if I had defined the current the other way, I'll have to pick up minus signs, otherwise I will be inconsistent in the two. So these two together just gives me L di dt equals minus I Ri plus V0, and let's pull minus R out, I minus V0 over R. Now this, I can change variable, I prime equals to I minus V0 over R. Then I've got L di prime dt is equal to minus Ri prime. And this is very easy to answer this question. This is I prime at time t, which is going to be I prime at time 0, e to the power minus R over L t. You can take a time derivative, R over L come down here, and then you can just say check. Okay, you can check that this will satisfy that, and then I can go back and write in terms of that. So I at t minus V0 over R equals I at 0 minus V0 over R. So that's this guy, e to the minus R over LT. And when I close the circuit, at that time the current was 0. So I at 0 is 0. So the current here is 0. So this will be 0, and so if I transfer over here, I of t is going to be simply V0 over R 1 minus e to the power minus R over L t. So that's the answer. That's for part A. Okay. Okay, so to get B, we don't need V0 value, because we're just looking for full current. So when you look at this, if you look at this formula, you have I of t at t. So when t goes to infinite, this goes to 0. So you have a maximum is over V0 over R. So that's the maximum. And so it starts at 0 and it asymptotically goes towards the maximum. So this is the IMAX. Okay. So just like before I said, so I can write this IT equals IMAX 1 minus e to the minus R over LT. And so I get, the question is 90%. So this, when I bring it over here, this is 0.9 for 90%. So you have a 0.9 equals to 1 minus e to the minus r. R is 10. So I'll put it later, the numbers. So that's, and how to solve for t. So you bring this on the other side. So e to the minus r over lt. 1 minus 0.9 is 0.1. Then you have to take a natural log of both sides. So minus r over lt, natural log of that. And so the other side, I'm going to have a natural log of 0.1. So the t, this is going to be 1 over 10. So this is going to be minus log of 10. Minus cancels out. So t is going to be L natural log of 10 over r. Okay, so putting the L and M. So L is in millihenry and R is in ohm. So 2 millihenry, and we have a 10 ohm, log 10. So you can see if it was a Henry and this, that will be second, has to be just from the units. So H Henry over ohm is second. Now milli will make it millisecond. So this is 0.2 log 10 millisecond. So let me just calculate that. Math dot log 10. Let's see how much that comes out. That's a correct. So let me see. 0.2 star math dot log, and so 0.46 milliseconds. So this is equal to 0.46 millisecond. That's the answer. Okay, so if you like this kind of explanation, please hit a like button so many more students can get directed to this website or this video. If I'm posting these kinds of videos once a day, one per day, approximately one per day, and you'd like to be notified when the new videos comes up, I'll appreciate you can subscribe to this channel. Tell your friends about this channel. That will be great. And there are a lot more of these problems solved in my website. So if you can go there, you can, this is a free textbook online. It's used by a lot of places. I'm still improving those websites, so some of them not completely done yet. I'd like to have, if you find any error or anything in a place, please let me know. I always encourage you to leave some comments at the end of the video. And that's it for now. Take care. Bye.